This is Mrs. Scarpel, and this video is going to cover arithmetic sequences and linear functions. With this example, we're working off of the diagram that has these figures. And as we look at these figures, we see that they always have these 5 squares, and each time one more is added on these other ends. So figure 1 has 1, 1, and 1. Figure 2 has 2, 2, and 2. Figure 3 has 3, 3, and 3, and so on. Now we're going to be looking at total number of squares. So figure number 1 has a total number of 8 squares. Figure 2, we added 3 more to get 11. And we can also show this on our table, that to go from 8 to 11. We had to add 3 more. 3 more were added for figure 3. And 3 more were added for figure 4. We call these 3's a common difference, which makes this a linear function. When you have a constant rate of change like we have here, we end up with a linear function. And we'll see this as we graph it. So I have my figure number on my horizontal axis, and I have my number of squares on my vertical axis. And I'm going to label these. I think I can go ahead and just go by 1. So 0, 1, 2, 3, 4, 5, 6. I know that's more than what's in the table. And then I'm going to label every other, so the 2's on my vertical axis. Remember, when you are labeling, you want to have equal spacing between your values, and you want to be going from one value to the next the same way, much like we do in this linear or this arithmetic sequence. 8, 10, 12, 14, 16, 18, and 20. So we know that figure number 1 has 8 squares. Figure number 2 has 11 squares. Figure number 3 has 14. Figure number 4 has 17. And if we look at this, from one point to the next, I'm going up 3 and right 1, up 3 and right 1, up 3 and right 1. So I could use the table to find what the next one by adding 3, but using the graph, I can go up 3 and right 1 as well to show that figure number 5 would have 20. And as we can see, because that rate of change was the same, that would be the slope of a line if I drew it through there. But because we have specific figures with a specific number of squares, I'm going to leave this as a discrete graph. I'm going to leave it with just the points because we don't have any partial figures. Let's take a look at writing some equations now. For the recursive equation, I'm going to use 1, 2, and 3, and the values are 8, 11, and 14. Our recursive equation, because I'm using n and f of n, I'm going to adjust my table here to represent the same. For our recursive equation, we're going to need to have a notation for previous, f of n minus 1, and plus some value. Well, we know what that value is. We know that that value is 3. So to get number 2, the previous value is 8, plus the 3 gives us the 11. For 3, where we have 14, we're taking the previous, which was the 11, and adding 3 to get 14. What we don't have is what did it take to get the 8 for term 1. So we can find that. What would I have to add to 3 to equal 8? I can ask myself the reverse. If I'm adding to go to the next one, then to go to my previous one, I want to do the opposite. I'll subtract 3. So 8 subtract 3 is going to be 5. That tells me that my 0 term has a value of 5. Now for my recursive sequence, it doesn't really matter if I start at 0 or if I start at 1. I still need to state what that first term that I'm using for my recursive is going to be. So we have f of 1 equals 8. F of n would equal f of n minus 1 plus 3, because that's how we find our next term. You could also write this as f of 0 equals 5, but the rest of it would not change. It would still be f of n equals f of n minus 1 plus 3. Let's take a look at the explicit. When we have the explicit function, we're going to write it in a linear form. Many students are aware of the slope-intercept form, y equals mx plus b. We're going to do function notation, so we will have that f of n will equal something n plus something. So that coefficient, that number in front of n, is our common difference, and what we end up adding to it is our y-intercept, which is why I was including the 0 on the previous slide, because in order to have a y-intercept, the x value, or the input value, needs to equal 0. So if I use my table and I use the values 0 through 3 so that I can, oops, wrote the wrong number, so that I can check to make sure my pattern is going to work, my explicit equation is going to work. So my common difference was 3. It increased 3 each time. So I'm going to have a 3n. Well, if I take 3 times 0, what would I have to add to it to equal 5? Well, I would have to add 5, because 3 times 0 is 0. If I do 3 times 1, I'm replacing the n value with my input values. That's 3. What do I have to add to it to equal 8? I'm adding 5 again. If I do 3 times 2 is 6, and I need it to equal 11, I need to add 5 to my 6. So as we can see, this next one should be 3 times 3 plus 5. So 3 times 3 is 9 plus 5 is 14. So our explicit equation is going to be f of n equals 3n, oops, I see I wrote it wrong up here, plus 5. The common ratio and the y-intercept. So So what can we take away from arithmetic sequences and linear functions? The graph is going to be a line or points that are linear. Linear functions or arithmetic sequences have a constant rate of change. We call that a common difference. Equations can be written in the form y equals mx plus b, but we will use function notation so that it's going to be f of n equals that common difference. I'll use d n plus the y-intercept. I'll go ahead and just use b again. The y-intercept is equal to the value of f of 0. Again, you want that input value to be 0 to know where you're going to cross the y-axis. The slope is the constant difference between terms. And that is our last one. And I'm just going to make a note here, this constant rate of change, I called that a common difference. So arithmetic sequences have a common difference, the value that we keep adding to our previous terms. And this concludes our brief review of arithmetic sequences and linear functions.